Welcome. So this set of videos describes Taylor polynomials and the related Taylor series for functions. And in this set of videos, I'll be assuming that you have completed preview activity 8.5.1. So it's written down on the first page of the handout after the instructions. So if you have not completed that activity, you can go ahead and pause the video and complete it now. So in this activity, it really motivates the main ideas with Taylor polynomials. So what we did is you looked at the graph of e to the x, or you consider the function e to the x, and you found the best linear function to match f of x near 0, and then you found the best quadratic function, the best parabola that matches f near x equals 0. And so what I want to start with now is looking at this graphically. And so let's go ahead and we'll go over to this Desmos sheet that I have listed here. And so when you open the sheet, you'll see that there are two functions graphed. There's one in blue and then a function in red. You can't actually see the function in red. It's hidden in this functions set of commands here. But what the red function is the best degree n approximation of the blue function. And so n equals 0, a degree 0 polynomial is just a constant function, so a horizontal line. And if we're trying to approximate near x equals 0, of course the best constant function is going to be the function 1. Then as you computed, you found the best line to approximate the exponential function, and so you found the slope of that line is 1, and it passes through the point 0, 1. And then in the preview activity, you additionally computed the formula for this parabola, the red parabola here, and you can see that does a better job, close to 1, of approximating the function e to the x. And here you can see by toggling back and forth that now there's some bend to the red curve that is matching the concavity of the blue curve. So if we wanted to continue this process, it's easy to imagine taking higher and higher degree polynomials, and that's what we're seeing here as you increase n, is we're seeing, and here what I have is the best 5th degree polynomial. The code here was a little bit cumbersome. I have some Maple code that I'll be doing a follow-up video in that will allow us to take higher degree polynomials than 10. So this code only goes up to 10. You can see here this n equals 5. Well, it looks like it's almost identical right here between x equals 1 and x equals 2. You start to see as we zoom in that, in fact, there still is some error out here to the right. And then, of course, you see there's a lot of error off to the left. But as we continue to increase the degree, these polynomials start to look closer and closer, closer and closer to e to the x. On larger and larger intervals, but that's something we'll be exploring more as well. Okay, so let's go ahead and summarize some of these observations. So we can, let's see, so the Desmos code plots polynomials of degree n to approximate f of x near x equals 0. And we plot these for n equals 0, 1, 2, 3, dot, dot, dot. Okay, and then as n increases, we notice that the graphs get closer and closer to the graph of f near x equals 0. And the term near is something, right, that it's a little bit relative. Okay, so let me go ahead and just give a definition. The degree n, all right, so maybe we'll start with the function. So let f be a function with n derivatives at a point x equals a, and we will define the degree n Taylor polynomial for f near, let me just go ahead and say centered at x equals a, is the polynomial whose say degree n polynomial whose whose function value and derivatives match f at a. And first n derivatives, so okay, so what you computed then is the degree 1 and degree 2 Taylor polynomials for the function e to the x. All right, and for posterity, let's just go through here and compute the other Taylor polynomials. So in fact, we can kind of continue the process. So with our example, and the functions that we're going to compute here, remember, are just the functions that we graphed in the previous, on the Desmos sheet that we were just on. So let's think about this example. F of x equals e to the x, okay? And what we know is if we want to say near x equals 0, right, then what we are thinking about is f of 0 equals 1, f of 1, sorry, let's see, we want to think about, okay, so let's first consider the function and its derivatives, right? So all of the derivatives are e to the x. And so then we need to evaluate these because these are the points we want to match. And so as you did in the preview activity, you know that f of 0 is equal to e to the 0, which is equal to 1. F of f prime of 0 is still equal e to the 0 equals 1, dot, dot, dot. Okay, so all the derivatives also at 0 have to equal 1. And so then the question is, what is the degree n Taylor polynomial, which has all of the derivatives equal to 1 and the function value equal to 1? And so we can write down a general form of the Taylor polynomial. So let's write this down. So we denote this as Pn of x. And I'm just going to start putting in some variables here. So C0 plus C1x plus C2x squared plus dot, 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 plus Cn x to the n. And so I am writing this in a slightly non-standard way because I have I've put the higher order terms on the right, but that doesn't really change it doesn't change the polynomial at all. I'm just doing that for convenience to match the calculations that you had done earlier. So, all right, so now if we think about this, Pn of x equals C0, what you did in the preview activity is I'm going to go ahead and switch colors to make this easier to follow. You plugged in here and you said, well, I know that Pn of 0 has to equal, C0, and then all of these terms with x's in them drop out. And so what we find then is that C0 equals 1. Okay, then we go on and we need to calculate the first derivative of this function. So Pn x prime, let's see. Yeah, so the first derivative of the Taylor polynomial is going to be, now when we differentiate, the first term C0 differentiates to 0 plus C1 plus 2C2 x to the 2 minus 1. I'm just going to write this a little bit inefficiently, but just so that we can kind of see the patterns that are happening here. Plus dot, 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 plus, and then this term is going to be n times C n times x to the n minus 1. And so rewriting this, we have that this is equal to C1 plus 2C2x plus, and the next one is going to be, I didn't write this term above, but let me just put it in here, 3C3x squared plus dot, 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 plus, let me go ahead and get this last one, n C n x to the n minus 1. Okay, so now we know that Pn prime of 0 has to equal, and now we can actually plug in here. We know that if we plug in x equals 0, all of the later terms in the polynomial will become 0. So we have Pn, we have the derivative at 0 is equal to just C1. And so we find that C1 is equal to 1. And so we have found now two of the, so our goal then is to solve for all of these coefficients, C0, C1, and so on. Right, so we'll just continue and recognize that you are doing some of the same calculations that you had done before. We'll talk about why that is in just a moment. So P n double prime. So now we're going to take the second derivative, and this is just 2c2 plus 3 times 2 times c3 times x, right? And so now, right, what I've done here is I'm taking the derivative of the first derivative. So the derivative of c1 is just 0, so that term goes away. The derivative of 2c2x is just 2c2, and then when I differentiate the next term using the power rule, I get a factor of 2 coming in. So, oops, pardon me, I think I just somehow moved this page. That was not what I intended to do. There we go. Thank goodness for undo. So I have 2c2 plus 3 times 2 times c3 times x plus, okay, let me add another term in here. So the next term is going to be 4 times 3 times c4 times x squared plus ... And then this last one, we're going to be differentiating here. We're going to have n times n minus 1 cn x to the n minus 2. Okay, so we can see the pattern here. I'm going to just very quickly go ahead and put in here p n double prime at 0 is then equal to 2 times c2. And we know that 2c2 has to equal 1. So this implies that c2 is equal to 1/2. If we continue one more time, and we'll just do this one more time, I really want the pattern to become apparent, and I'm going to ask you to do something similar coming up. And so I'm going to just, for 3, instead of putting 3 dashes for the third derivative, I'll just put the 3 in parentheses, as you see here. So the third derivative is just going to be, well, this constant term in the beginning goes away, and then we're left with 3 times 2 times c3 plus 4 times 3 times 2 c4 times x plus what's going on here? I'm going to delete this thing. Okay, 4 times 3 times 2 times c4 x plus 5 times 4 times 3. And maybe to make things even more apparent here, I can go ahead and put 3 times 2 times 1 times c3. Okay, so each of these terms here has 3 different numbers multiplied. So then I have oops, what's going on here? I'm wondering if my Apple Pencil is running out of I almost said ink, but out of battery. Okay, so here's c5 x squared plus ... And the last term is going to be n times n minus 1 times n minus 2 times cn times x to the n minus 3. So I wanted to do this many terms so that you can really start to see the pattern that arises. And when we go in here and we evaluate this at 0, we have p, and this third derivative evaluated at x equals 0 is equal to, and now all of the later terms again are equaling 0. So this is equal to 3 times 2 times 1 times c3. And we know that this is equal to 1. And so if we solve for c3, c3 is equal to 1 over 3 times 2 times 1. And our compact way of writing that is just 1 over 3 factorial. So let me go ahead and just add another blank page in here. So, so what we're seeing then, what happened? Did I just lose my extra page here? Undo. Okay, good. So let's go ahead and add a page. I think I deleted a page instead of adding. So okay, so at this point now, we've solved for C3, and so we can continue in this fashion, and we can write down just by matching these patterns, right? I can write down P, and let's talk about the kth derivative with respect to x. Well, so notice here that every time I take a derivative, we apply the power rule, and so I should be getting another. Term multiplied here, right? So let's notice, right, that in this P3 I have 3 times 2 times 1 in the first term, and then there's 4 times 3 times 2 in the second term, times the C4, of course. But each of these constants that I'm underlining here comes from one of the derivatives that I'm taking here, right? So the kth derivative is going to result in k times k minus 1 times ... all the way down to 1 times C3 plus, and then the next term is going to start with k, let's see, the next term is going to start with k plus 1 times, okay, and then the terms there are going to go all the way down to 2 times C, and I apologize here, this was not what it should have been. This should be CK, okay, and then the next term here is going to have, so there are K numbers here, right, and K numbers here. From the K different derivatives that we've taken. Okay, and then this is CK plus 1, and there is just an X here, right? So notice, just pattern matching, right, that the polynomial P3 has a term, a constant term, a term with an X, a term with an X squared, all the way up to n minus 3. So the kth derivative is going to have a constant term, an X term, all the way up to, the last one is going to have a term that is x to the n minus k. And we'll have Cn, and the constant out front will be n times n minus 1, ... and the last one is going to be n minus k. Actually, that would not be quite right. It should be n minus k plus 1. So you see how I can add another, oops. just move this over here. So this should be n minus k plus 1. And again, there are k numbers here in this product. And as we continue on down, then let me go ahead and just write p n k of 0 is equal to k factorial times ck, which is equal to 1. And when we solve for that, we end up seeing that ck is equal to 1 over k factorial. And if we continue here and we use, and we just look at the very last term, right? So this formula will hold also for k equals n, but let me just go ahead and write it in here because this is the last one. So Pn, the nth derivative of Pn, is going to just have one term in it, and it's going to be this term n times n minus 1 times dot dot dot, and the last term here will be n minus n plus 1. So what I'm doing here is I'm just thinking about plugging in here n minus n plus 1, so the last term is going to be a 1, and times Cn, and of course we've differentiated all the powers of that x away, so this is just a constant. So then what we see is that Pn of n 0 is equal to n factorial Cn, and this implies that Cn is equal to 1 over n factorial. Okay, great. So we have just done a giant computation here, and I want to remind you what we have actually figured out now. What we've now figured out is a formula for the Taylor polynomial of degree n, right? So this is, we now can write down the Taylor polynomial. What exactly, we can write it down. So we wrote it down here, but we had to use these constants c, and now we've actually solved for all of those. So, so let's go ahead and record our computation here. The Taylor polynomial of degree n, centered at 0, is equal to, I just wanted to make sure I had written x equals 0 up there instead of the arbitrary x equals a. So the Taylor polynomial of degree n centered at x equals 0 for f is, okay, and here in this particular case, let's say, let me go ahead and let's just be specific. E to the x is Pn of x is equal to, okay, so C1 was 1. Sorry, C0 was 1, C1, and let me go ahead and just write here 1 times x to the 0 plus 1 times x to the 1 plus 1/2, right? So remember, C2 is 1/2, so we're putting in 1/2 times x squared here. So we have 1/2 x squared plus, and then we found C3 was 1/3 factorial, so plus 1/3 factorial x cubed, and so on. Plus 1/n factorial x to the n. And so these are what these polynomials are that are approximating the function e to the x to higher and higher degrees of accuracy. So I had mentioned that so I want to bring this back to the preview activities that you have done. And so let's just notice here that in the process of computing Pn of x, right, when we compute successively higher degree polynomials, the initial terms don't ever change. And that should make sense to you because if we were to change any of the coefficients in the lower degree terms, then those smaller derivatives would not match anymore f of x. So what you should be seeing here is that because we're matching more and more derivatives, we're essentially just adding those higher order terms to the Taylor polynomial. And so what you can see then here is that, of course, the first 3 terms should match your quadratic, and of course the first 2 terms match your linear function that you had created. So I just want to follow up one more time about the activity. The preview activity 8.3.1 that I had told you a while back would be an important one to be thinking about, and I didn't really follow up a ton there. But what you did in that preview activity is you said, well, let's approximate e to the x by polynomials of higher and higher degree. And then what you did is you used those approximations to get a series that converges to the number e. Right, and so how did you do that? You said that that e to the 1 is equal to e, right? And so that is equal to, if f of x is e to the x, right, that's just f of 1. And you said that, and so then we were considering the fact that p0 of 1, p1 of 1, p2 of 1, etc. is a sequence that approaches e, right? And I can even be a little bit more explicit here, right? If we're thinking about Pn of x, now we know that it has this particular format here that we've written down. And so we can even say, right, that here our x is equal to 1, and so we were using the fact that that the sequence approaching e, well, let's write that not as, so these are actually, let me just be very careful because I know that I don't want you mixing sequences and series. This is a sequence of partial sums, right? Because we're adding more and more terms. So this is a sequence of partial sums that approaches E, right? So the partial sums are partial sums of the following series, right? So the series that is 1 plus 1 plus 1/2 plus 1 over 3 factorial plus 1 over 4 factorial plus ... And I'm going to go ahead and write this in sigma notation. This is the sum of 1 over x factorial, sorry, not x factorial. I'm going to use k factorial from k equals 0 to infinity. And so we used these facts, but we used them just for series of numbers. So we used these approximations to get a series of numbers, which we found converges to E. And if you'll recall here, we define 0 factorial to be equal to 1, so that that first term will make sense there. Okay, so what is all this? So the connection I wanted to make with all of this is that that we've now used those same polynomial approximations, but instead of just getting an approximation of a single number, we actually get an approximation of the whole function. So we're essentially doing the work of approximating e to the x for any x at the same time. Right? So this is a really powerful idea here, to be not thinking about a series of numbers, but in this section, what's new is we expand our viewpoint to think about series of numbers. Okay, and we haven't quite got to the series yet. We're still at the point in these videos where we're still thinking about specific polynomials, but where we're headed is to be thinking about series of numbers. So I'd like to go ahead and stop here. I think this is I kind of jumped a little bit ahead. I want to give you a chance to compute some small order Taylor polynomials near 0. And so I have some, this is activity 8.5.2, to calculate a few of these. So I will go ahead and stop this video, and we'll resume after you have done that activity.